For more than a century, asphalt has been the default answer to a simple question. How do you build a road that lasts? Black, sticky, cheap to pour, and everywhere you look, from the smallest village lane to the biggest highway system on Earth. But in China right now, engineers are quietly walking away from that answer. They are pouring roads that do not crack in the summer heat, do not crumble under snowplows, and in some cases, generate their own electricity while cars drive over them. Some of these roads even melt ice on their own, without a single truck spraying salt. When foreign engineers visited to see the technology firsthand, several of them admitted they did not believe it was possible until they stood on the surface themselves. This is the story of how a country obsessed with speed and scale decided that the material holding up its entire transportation network needed to be reinvented from scratch, and how that decision is now rippling out to reshape how the rest of the world might build roads in the future. To understand why this shift is such a big deal, you first have to understand just how much the world depends on asphalt, and how strange it is that something so common has so many hidden weaknesses. Asphalt feels like it has been around forever, but the version we drive on today did not really take off until the 20th century, when oil refining made it cheap to produce at massive scale. It is basically a mixture of crushed rock, sand, and a sticky black substance called bitumen, which is a byproduct of oil refining. Mix them together, heat it up, roll it flat, and you get a smooth, black surface that can be laid down fast and cheap. That combination of speed and cost is exactly why it became the global standard. If you needed to connect two cities with a road, asphalt let you do it in weeks instead of months. But asphalt has always had a dirty secret. It is a material that is constantly fighting a losing battle against the weather. In the summer, when temperatures spike, asphalt gets soft. Heavy trucks can leave ruts and grooves in a road simply because the surface temporarily behaves more like putty than solid rock. In the winter, the opposite problem shows up. Asphalt becomes brittle in extreme cold, and water that seeps into tiny cracks expands as it freezes, prying the surface apart from the inside. This is why cities in cold climates spend an enormous portion of their infrastructure budget every single year just patching potholes that appeared over a single winter. Then there is water damage in general. Asphalt is not fully waterproof. Rain seeps down through microscopic gaps, and over years, that moisture weakens the layers underneath, causing the road to sink, buckle, or develop the kind of cracks you see spreading out like spiderwebs across old parking lots and highways. Add heavy traffic, and you get a surface that typically needs a full repaving job somewhere between 8 and 15 years, depending on climate and traffic load. Multiply that repair cost across an entire country, and you start to see the real cost of asphalt is not the material itself. It is the constant, expensive, disruptive cycle of tearing it up and redoing it. There is another cost that rarely gets discussed outside of transportation ministries, and that is the price of simply shutting a road down. Every time a crew needs to repave a stretch of highway, that section either closes entirely or gets reduced to a single lane for weeks. For a country moving as much freight as China does, a single closed lane on a major freight corridor can ripple outward into delayed shipments, backed up ports, and factories waiting on parts that are sitting in traffic instead of arriving on schedule. When engineers started building the case for smarter road materials, this hidden cost of disruption became one of their strongest arguments. Because a road that needs to be repaved half as often is not just cheaper to maintain, it is also a road that stays open twice as long. China's road network is not small. It is the largest highway system in the world by total length, with hundreds of thousands of kilometers of expressways connecting cities that did not even have proper paved roads a few decades ago. For a country expanding infrastructure at this scale and this speed, the ongoing cost of maintaining traditional asphalt became a problem too large to ignore. Every closed lane for repairs meant lost time, lost shipping, and lost money moving through the world's most active manufacturing economy. So a question started forming among engineers and material scientists working on China's infrastructure. What if the surface of the road itself could be smarter? Not just a passive layer of rock and tar sitting there waiting to crack, but an active material that could resist heat, resist cold, repair itself, and maybe even do something useful beyond just supporting weight. That question is what set off years of research that eventually produced several breakthrough road materials now being tested and rolled out across the country. And the first of these breakthroughs came from a place you would not expect. Not a chemistry lab, but a solar power research facility. Around the middle of the last decade, Chinese engineers began experimenting with what became known as solar roadways, roads embedded with photovoltaic panels directly built into the driving surface. The idea sounds almost absurd at first. Put solar panels under a layer tough enough for an 18-wheeler to drive over, and somehow keep them generating power. But the logic behind it made sense once you thought about the scale involved. China has hundreds of thousands of kilometers of exposed road surface sitting in direct sunlight for most of the day, completely unused as anything except a place for tires to roll. Engineers realized that surface was essentially wasted real estate. If even a fraction of that road space could double as a power generation source, it could feed electricity directly into nearby streetlights, toll booths, electric vehicle charging stations, or the regional power grid. The first major test came on a stretch of highway in Jinan, in Shandong province, where engineers laid down a 1-kilometer section of solar road as an experiment. The design used 3 layers. On the bottom sat the solar panels themselves, wired together to collect and transmit power. In the middle was an insulating layer to protect the electronics from moisture and pressure. On top was a specially engineered, transparent concrete, strong enough to handle vehicle weight while still letting sunlight pass through to the panels below. This transparent top layer was actually one of the hardest problems to solve. Regular glass would shatter under truck tires within days. Engineers needed something that could let light through like glass, but behave structurally more like reinforced concrete. After extensive testing, they landed on a special resin-based composite embedded with tough, transparent aggregate, strong enough to withstand the constant pounding of tires, sharp temperature swings, and years of ultraviolet exposure without clouding over or cracking. The results from that first kilometer were promising enough that engineers began planning larger installations, but they also uncovered problems that needed fixing. Dust and grime built up on the surface, blocking sunlight and reducing power generation. Heavy truck traffic caused faster wear than expected in certain sections, and theft became an unexpected issue, with some panels reportedly stolen from an early test site before proper security measures were installed. Rather than abandon the idea, engineers treated these failures as data. They adjusted the surface texture to reduce dust buildup, reinforced weak points in high traffic zones, and improved installation techniques to make the panels far harder to remove. What emerged over several iterations was a road surface that could realistically survive years of exposure while consistently producing usable electricity. It is worth pausing here to appreciate just how unusual this approach is in the history of infrastructure engineering. Most countries treat a failed pilot project as proof that an idea does not work, and they move on. But the Jinan test was treated internally, not as a verdict, but as a single data point in a much longer experiment. Engineers went back, adjusted the resin mixture, changed the surface texture to shed dust more effectively during rainfall, and reinforced the edges of each panel section, where cracking tended to start first. It took several redesigns before the material behaved the way the original concept promised. And that willingness to keep iterating rather than declare the whole idea a failure is arguably the real innovation here, more than any single material breakthrough. But solar roads turned out to be just the opening chapter. While that research was happening, an entirely separate group of engineers were tackling a different problem: ice. Winter road maintenance is one of the most expensive and dangerous parts of running a modern transportation network. Ice on a highway does not just slow traffic down, it kills people. Every winter, thousands of accidents happen because a driver hits a patch of black ice they never saw coming. The traditional solution has always been salt trucks, sand trucks, and plows working around the clock during storms. An approach that is labor-intensive, environmentally damaging to nearby soil and waterways, and still leaves roads dangerous in the hours before crews can respond. Chinese researchers began exploring a strange but elegant alternative. What if the road itself could generate just enough heat to prevent ice from forming in the first place? The concept borrowed directly from the solar road research happening in parallel. If you could embed a heating element into the road surface, powered either by the sun or by grid electricity during off-peak hours, you could keep the pavement a few degrees above freezing during exactly the conditions when ice becomes a hazard. Engineers tested several approaches, including embedded electrical heating wires similar to those used in heated driveways for homes, as well as more advanced systems using carbon fiber composite materials that generate heat when a small electrical current passes through them. The carbon fiber approach proved particularly interesting because it could be manufactured as thin sheets, laid beneath the surface layer without dramatically increasing the total road thickness or weight. A notable pilot project tested this heated pavement technology on a bridge deck in a colder province. An especially smart choice because bridges freeze faster and more dangerously than regular roads. Bridges lose heat from both the top and bottom surfaces since they are surrounded by open air rather than insulated by the earth underneath like a normal road. That means bridge decks often ice over even when the surrounding roads are still perfectly safe, catching drivers off guard right when they least expect it. The heated bridge deck maintained a surface temperature just above freezing during test periods, successfully preventing ice formation without a single truck needing to spread salt or sand. Engineers monitoring the pilot reported that even during snowfall, the heated surface stayed clear, while surrounding untreated sections accumulated a slippery layer within minutes. The implications of this technology stretch well beyond convenience. Salt used for winter road treatment corrodes vehicle undercarriages, damages bridge reinforcement steel over time, and washes into nearby soil and water systems, harming plant life and aquatic ecosystems. A road that simply does not need salt in the first place sidesteps an entire category of long-term infrastructure damage and environmental harm. There is a financial angle to this as well that transportation departments rarely advertise. Salt is not free, and neither is the labor to spread it. A single province can spend enormous sums every winter just purchasing rock salt and running fleets of trucks around the clock during storms. Heated pavement carries a steep upfront installation cost, but when engineers ran the numbers over a 15 to 20-year window on the highest risk bridge sections, the math started tilting in favor of the heated surface, especially once you factor in the reduced accident rate and the insurance and liability costs tied to winter crashes on exposed bridge decks. But heating an entire national highway network is not currently realistic in terms of energy cost, so engineers have focused deployment on the highest risk locations: bridge decks, mountain pass roads, and sharp curves in regions with heavy winter weather, exactly the spots where a single icy patch causes the most accidents. Rather than trying to heat every road in the country, the strategy has been surgical, targeting the small percentage of road surface responsible for a disproportionate share of winter accidents. While solar generation and self-heating pavement were being developed, a third, and in some ways even more ambitious project was underway. Engineers wanted a road surface that could heal its own cracks. This idea sounds like science fiction, but the underlying chemistry is surprisingly grounded. Traditional asphalt cracks, because the bitumen binding the rock and sand together gradually oxidizes and stiffens over years of sun exposure, losing its flexibility. Once it becomes brittle, cracks form, water gets in, and the freeze-thaw cycle tears the surface apart from within. Researchers began experimenting with self-healing asphalt using two main approaches. The first, involved mixing tiny steel fibers into the asphalt itself. When cracks begin forming, a specialized induction heating machine can be driven over the road surface, generating a magnetic field that heats the embedded steel fibers just enough to soften the surrounding bitumen. This allows the material to flow back together and reseal small cracks before they grow into potholes, essentially giving road crews a way to reset the material's flexibility without tearing up and repouring the entire surface. The second approach used microcapsules containing a rejuvenating oil mixed directly into the asphalt during production. As tiny cracks form and begin to spread through the material, they physically rupture these microscopic capsules, releasing the rejuvenating oil directly into the crack. That oil re-softens the surrounding bitumen, allowing it to flow and reseal the gap, similar to how a scab forms over a wound. Both approaches share the same underlying goal: extending the usable lifespan of asphalt by giving it a way to repair minor damage before it becomes major damage. Early field tests on sections of self-healing asphalt showed cracks that would normally have required a maintenance crew, instead resealing on their own within days of forming, particularly when combined with periodic induction heating maintenance passes. For a country managing hundreds of thousands of kilometers of pavement, even a modest extension in road lifespan translates into staggering savings, potentially delaying full repaving cycles by years on high-traffic routes. At this point, you might be wondering how all these separate innovations, solar generation, self-heating surfaces, and self-healing materials, actually come together in the real world. The answer is that Chinese engineers began combining them into integrated smart highway pilot projects, treating the road surface less like a passive slab of material and more like a piece of infrastructure technology with multiple functions layered on top of each other. One of the most widely discussed pilot projects combined solar panel embedded lanes for power generation with sensor systems built directly into the road surface. These sensors could detect vehicle weight, speed, and even weather conditions in real time, feeding that data back to traffic management centers. In theory, a smart highway equipped this way could automatically detect ice forming in a specific section and activate localized heating elements exactly where needed, rather than heating an entire stretch of road constantly regardless of conditions. The sensor data also opened up possibilities for dynamic traffic management. If a section of road could detect that a truck was carrying an unusually heavy load, or that traffic density was approaching dangerous levels, that information could feed directly into digital road signs and traffic light systems further down the route, adjusting speed limits or rerouting traffic before congestion or accidents happen. Some pilot corridors even experimented with wireless charging strips embedded beneath the surface, designed to charge electric vehicles as they drove over specific lanes, a concept that could eventually reduce the need for as many stationary charging stations if scaled up successfully. The wireless charging idea in particular has attracted attention from engineers outside China because it addresses a problem that pure electric vehicle adoption keeps running into. Charging infrastructure is expensive to build and takes up space, and drivers still have to stop and wait, even if only for a short time. Early tests embedded coils beneath a short stretch of road, tuned to transfer power wirelessly to a receiver mounted on the underside of specially equipped test vehicles. The efficiency of that power transfer is still lower than a direct plug-in charger, but engineers view it as a technology that could make the most sense on short, heavily trafficked corridors like airport access roads or bus routes with predictable, repeated paths. None of this happened without setbacks. Engineers working on these projects have been candid, at least within technical publications and conference presentations, about the challenges involved. The transparent concrete used in early solar road sections needed multiple redesigns before it could reliably survive heavy truck traffic without clouding or cracking. Heating elements embedded in bridge decks required careful engineering to avoid uneven heat distribution that could actually create new weak points in the concrete structure itself. And the cost of embedding sensors, wiring, and electronics into every meter of road surface remains far higher than traditional paving, meaning widespread rollout across the entire national highway system is still years away rather than months. But the direction of the research is clear, and it represents a fundamental shift in how China thinks about the humble road surface. Instead of viewing pavement as a disposable material that wears out and gets replaced on a predictable cycle, engineers are increasingly treating it as a piece of long-term infrastructure technology, something that can generate power, resist damage, and actively respond to conditions rather than passively deteriorating under them. This shift did not happen in isolation. It reflects a broader pattern in how China approaches infrastructure development generally, treating massive public works projects as opportunities for technological experimentation rather than simply repeating the same construction methods used decades earlier. The same instinct that led to the world's most extensive high-speed rail network, built largely within the past 2 decades, is now being applied to something as seemingly mundane as the surface layer of a highway. International engineers who have visited these pilot sites have generally reacted with a mixture of skepticism and genuine surprise. Skepticism, because the cost of these advanced materials remains significantly higher than traditional asphalt, and questions remain about long-term durability under the most extreme traffic loads over many years, rather than the shorter pilot testing periods conducted so far. But genuine surprise as well, because several of these technologies work exactly as advertised in the specific conditions they were tested under, generating measurable power, preventing ice formation, and extending crack resistance well beyond what traditional materials achieve. Some Western infrastructure researchers have pointed out that similar solar road concepts were actually tested in other countries earlier, including a widely publicized experimental solar road project in France that ultimately underperformed and was quietly discontinued after a few years due to durability problems and lower than expected power output. This comparison raises a fair question. Why would China's version succeed where an earlier attempt elsewhere fell short? Part of the answer comes down to iteration and scale. China's approach has involved building multiple test sections across different provinces with different climates, learning from failures in each one, and refining the material composition and installation technique repeatedly, rather than a single large-scale attempt in one location. The transparent concrete formula alone reportedly went through several major revisions based on data collected from early pilot sections before engineers settled on a version durable enough for continued expansion. Another part of the answer is patience with the economics. Rather than expecting solar road sections to become profitable immediately, the strategy has treated early installations explicitly as long-term research investments, accepting higher upfront costs in exchange for data that improves the next generation of materials. This mirrors the same strategy China used with electric vehicle battery technology, subsidizing early development at a loss until manufacturing scale and technical refinement brought costs down to competitive levels. There is also a simple matter of national infrastructure priorities. Countries with slower-moving public works budgets and more fragmented regional authority over road construction face real practical barriers to funding this kind of long-term experimental infrastructure research. China's centralized planning process, whatever criticisms exist about it in other contexts, does allow for large-scale coordinated pilot testing across multiple provinces simultaneously, generating far more comparative data in a shorter period of time than would typically be possible in countries where road construction decisions are made independently by dozens or hundreds of separate local governments. It also helps that China's manufacturing base for the components involved, from photovoltaic cells to carbon fiber composites, already exists at massive scale for other industries. A country that produces the majority of the world's solar panels for rooftop and utility-scale installations does not have to build an entirely new supply chain to source panels for a road project. That kind of existing industrial infrastructure lowers the cost of experimentation dramatically compared to a country that would need to build a specialized supply chain from nothing just to test a handful of pilot road sections. So, where does this leave the future of asphalt itself? It would be an overstatement to say asphalt is disappearing entirely. The vast majority of roads currently being built in China and around the world still use traditional asphalt, simply because it remains the cheapest and fastest option for covering enormous distances of low-traffic, rural roads and secondary routes where advanced materials are not economically justified. But for the highest traffic corridors, the most accident-prone winter routes, and the busiest urban expressways, the calculation is shifting. When you account for the true long-term cost of asphalt, including repeated repaving cycles, winter salt damage, accident costs from ice-related crashes, and constant maintenance disruption to traffic flow, advanced materials that cost more upfront but require dramatically less ongoing maintenance start to look like the more economical choice over a 20 or 30-year lifespan rather than an 8 to 15-year cycle. Engineers involved in these projects have suggested that the next decade will likely see continued expansion of smart road technology, specifically targeted at these highest value locations. Mountain pass highways in provinces with severe winter weather, bridge decks nationwide, given how disproportionately dangerous bridge icing has proven to be. Urban expressways with extremely high daily traffic volume, where even small extensions in surface lifespan translate into massive savings at scale. And potentially, longer term, sections of highway near major solar energy initiatives, where the power generation potential of embedded solar roadways could meaningfully contribute to regional grid capacity. There is also growing interest from other countries watching these pilot projects closely. Delegations from several nations with severe winter climates have reportedly visited Chinese pilot sites specifically to study the heated bridge deck technology, given how directly applicable it is to their own infrastructure challenges. Whether or not other countries adopt the exact same materials and methods, the research itself is likely to influence global conversations about road technology moving forward, the same way China's high-speed rail expansion influenced rail infrastructure discussions in countries that had not built new rail lines in decades. It is worth noting that adoption elsewhere will not be instant, even if the technology proves itself completely. Road construction standards, government procurement rules, and existing contracts with asphalt suppliers are deeply entrenched systems in most countries, built up over decades of doing things one particular way. Shifting away from that system requires more than just proving a technology works in a lab or even in a pilot stretch of highway. That kind of institutional inertia is often the real barrier standing between a promising pilot project and widespread adoption, more so than any remaining technical hurdle. What makes this story genuinely interesting is not just the specific technologies involved. Impressive as they are, it is the underlying mindset shift. For over a century, the road beneath our tires has been treated as one of the most boring, unchanging pieces of infrastructure imaginable. Pour it, roll it flat, drive on it until it cracks, then repeat the entire process. China's engineers looked at that century-old assumption and asked a genuinely disruptive question: what if the road itself could do more? That question led to pavement that generates electricity from sunlight passing through its own surface. It led to bridges that keep themselves ice-free without a single salt truck. It led to asphalt embedded with steel fibers that can be reheated and resealed rather than torn out and replaced. None of these ideas individually reinvents the entire concept of a road, but together, they represent a meaningful shift away from treating pavement as disposable and toward treating it as active infrastructure. Something engineered not just to survive traffic, but to actively contribute value while doing it. Whether this approach eventually replaces asphalt on a global scale, or simply carves out a permanent niche on the highest value roads where the economics justify the extra cost, one thing is already clear. The assumption that roads have to be dumb, passive slabs of black material sitting there waiting to crack is no longer automatically true. And once an assumption like that gets broken in one country, it tends not to stay contained for very long. The next time you drive over a smooth stretch of highway and think nothing of it, It is worth remembering that somewhere in China right now, engineers are testing a version of that same stretch of road that generates power while you drive over it, melts the ice before your tires ever touch it, and quietly heals its own cracks while traffic keeps moving above it. The road, as we have always known, it may be a lot closer to obsolete than most drivers realize. If this kind of engineering story is the kind of thing you find fascinating, there is a lot more of it out there, and it is worth paying attention to how quickly some of these ideas move from experimental test sections to standard practice once the economics finally line up.